Sequences. An infinite sequence is an ordered list of numbers, and we separate the numbers by commas. So for example, we could have the sequence 2, 4, 6, and so on. Each number, a with a subscript of n, is a term of the sequence, and the subscript n is called the index variable. So here, the first term is 2, so we'd call that a sub 1. We don't say subscript, we just say a sub 1, then 4 is a sub 2, and 6 is a sub 3, and so on. Now, a sub n represents the general term, the rule for finding the nth term. So on this sequence, hopefully we can see this is just even numbers. So the rule for finding the nth term is just 2 times the subscript n. So here the subscript is 1, and every sequence has a starting subscript of 1. So 2 times 1 gives us 2, 2 times 2 gives us 4, 2 times 3 gives us 6. So if I want the nth term, then I'm just going to multiply 2 times the subscript n. Other notations for a sequence include putting that general term inside braces and clearly indicating that the starting subscript is n equals 1 and going up to infinity. Or it's really just implied that a sequence starts with a subscript of 1 and is infinite, so we can just drop that piece on the side and simply put the general term a sub n in braces. Or we can list out all of the terms separated by commas. We can put the general term in there and in braces again. Now let's consider the infinite ordered list 1, 4, 9, 16, 25, and so on. Hopefully we can notice the pattern here is that 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared. So in other words, 1 squared is a sub 1, 2 squared is a sub 2, 3 squared is a sub 3, and then we have a sub 4, a sub 5. So we can write the nth term here as n squared. So the explicit formula for a sub n is n squared. So we can write this sequence as n squared in braces from n equals 1 to infinity, or just simply in braces n squared. Now, sometimes sequences are defined by explicit formulas, where a sub n is equal to f of n for some function f of n with positive integers as the domain. So notice that we only substituted in 1, 2, 3, 4, 5 positive integers. So in other words, sequences are what we call discrete functions, which are functions defined only for specific isolated values of the input and does not include all values in between. So we're going all the way, we're jumping from 1 to 2 instead of every single value in between, as opposed to continuous functions, which definitely are defined for every single value in between. Now let's compare discrete and continuous functions graphically. So an example of a discrete function, again, is the sequence a sub n equals n squared. On a sequence, we only substitute in the positive integers. So we go ahead and start at an input of 1 as our n value. 1 squared is 1, so we have 1, 1 as a point. Then I jump all the way to 2. 2 squared is 4, so 2, 4 is a point. And then 3 squared is 9, so 3, 9 is a point. So these are the only outputs so far for the discrete function a sub n equals n squared. This sequence is just these points. We're not going to connect them together. As opposed to the continuous function f of x equals x squared, well, what do we know about that? That's a parabola. And that parabola has a domain of all real numbers. So informally, it's continuous, so we can put our pencil down and draw it without ever lifting it up, versus our discrete function is just these individual points. So it's defined for only specific isolated values. Let's find a sub 1, a sub 2, a sub 3, and a sub 4 if a sub n is equal to the quantity negative 1 raised to the n plus 1 all over 2n plus 1. So what we're going to do is start with finding a sub 1. We're going to substitute in 1 into each n. So we're going to have negative 1 to the 1 plus 1 over 2 times 1 plus 1. So I have negative 1 squared over 3. Since I have a negative value to an even power, that's going to end up positive. So my a sub 1 is positive 1/3. Then a sub 2 is negative 1 to the 2 plus 1 over 2 times 2 plus 1. Now this time I'm going to have negative 1 to an odd power. And so a negative to an odd power will stay negative this time. And then in the denominator we have 5. So we end up with negative 1/5. Then a sub 3, we're going to have negative 1 to the 3 plus 1 over 2 times 3 plus 1. So I'm going to have negative 1 to an even power. And a negative to an even power is positive. And then over 7. So I'm going to have positive 1/7. Now hopefully we can start to see the pattern. The terms are going to alternate in sign, and that's because of the negative 1 in parentheses to the n plus 1. That's going to make our terms alternate. And then if you focus on the denominators, these are odd numbers. So 3, 5, 7. So hopefully we can recognize that a sub 4 would end up being negative 1 over 9. So if we do the work on that, we're going to see we have a negative to an odd power, and then 2 times 4 plus 1, and that is 9. So here we can go ahead and list them out. So we have 1/3, negative 1/5, 1/7, negative 1/9, and so on. Here we have a graphical representation of that sequence, that discrete function. So we can see 1/3, negative 1/5, positive 1/7, negative 1/9, and that those terms are going to alternate and bounce back and forth above and below that horizontal axis. But what's happening is they are getting closer and closer to 0 as n values approach infinity. So it looks like the limit as n approaches infinity of a sub n is 0. In this example, we want to find a sub n given the first few terms of a sequence. So we are given a sub 1, a sub 2, a sub 3, and a sub 4. And again, we need to find the a sub n general rule. So here, let's split it up and focus on the numerator and denominator. Notice that the numerator just matches the subscript. So the numerator general rule is going to be just n. Whatever the subscript is, that's going to become the numerator. And then let's focus on the denominator here. So the first number that we would substitute in is the subscript 1, and I have to get out a value of 2. For the second term, if I substitute in 2, I have to get out 3, a number that's 1 higher, just like how 2 is 1 higher than 1. And if I substitute in 3, I'm going to get out 4. So the pattern is that I'm always going to add 1 to the n value. So a sub n, the general term, is n over n plus 1. So let's say we wanted to find the 7th term, then that's going to be 7 over 8. On this example, if we, again, graph the terms of the sequence, which again is a discrete function, we can see those points 1/2, 2/3, 3/4, 4/5, 5/6, and so on. And it looks like as n approaches infinity, those function values are getting closer and closer to that y value of 1. Now let's talk about convergence or divergence of a sequence. If we're given a sequence a sub n, if the limit as n approaches infinity of a sub n exists, meaning the limit is a real number value, then we say that a sub n converges. So in our last two examples, the limit as n approaches infinity was 0 in one example and 1 in another example. Since those are real numbers, those limits exist and those sequences converge. But if the limit as n approaches infinity of a sub n does not exist, then we say that a sub n diverges. Now we have a theorem that says if f of n is equal to a sub n, where n is an integer, and the limit as x approaches infinity of f of x is equal to L, then the limit as n approaches infinity of a sub n is equal to L. So what's going on here? This basically says that towards infinity, the continuous function f of x and the discrete function a sub n, they have that same end behavior. So what we already know how to do from our Calculus 1 classes is evaluate a limit as x approaches infinity of a continuous function, and it turns out that the discrete function towards infinity is going to have the same limit behavior. Here's a quick example. Does the sequence n squared, written out with a few terms as 1, 4, 9, 16, 25, and so on, converge or diverge? Well, since the limit as x approaches infinity of x squared, the continuous function, goes to infinity, we know that the limit as n approaches infinity of n squared, the discrete function, also goes to infinity. And that does not exist. That's not a real number. So the sequence diverges. And hopefully we could see that by seeing the terms listed out, because these numbers are getting bigger and bigger and bigger, so they're not going to get close to any one real number. Now we have another helpful theorem. If the limit as n approaches infinity of the absolute value of a sub n equals 0, then the limit as n approaches infinity of a sub n equals 0. So this is going to help us when we're looking at sequences that have some negative terms. So let's say we have the sequence a sub n is equal to negative 1 to the n plus 1 over 2n plus 1. Because we have this negative 1 to the n plus 1, we know our terms are going to alternate in sign. Some are going to have negatives in front. Well, what we can do is just get rid of that and think about this numerator to be just positive 1 instead. And notice that if we take the limit as n approaches infinity of just 1 over 2n plus 1, here the top is constant and the bottom is a function of n, so towards infinity, this limit is going to go to 0. So we're looking at the limit of the absolute value of a sub n. And that matches up with the graph that we have right here. So this is the graph of the absolute value of a sub n. We've made all of those values positive, and we can observe they're getting closer to 0. And if we were to have looked at the limit of the terms that are bouncing between positives and negatives, so if we keep negative 1 to the n plus 1, our terms are still going to get closer to 0 as my n values get bigger. So the limit as n approaches infinity of the ones that include negative terms is still going to 0. So this is going to allow us to look at the positive only limit instead of thinking about them alternating in sign. And now we're going to look at some limit properties for sequences. And really all this is going to do is allow us to use the same limit properties that we did for continuous functions for discrete functions. So as long as we have sequences a sub n and b sub n, and any real number c, as long as the limit as n approaches infinity of a sub n exists and equals a, and the limit as n approaches infinity of b sub n exists and equals b, then all of these limit properties hold. The limit as n approaches infinity of a constant is just that constant. If we take the limit as n approaches infinity of a sub n plus or minus b sub n, that's going to equal just a plus or minus b. The limit as n approaches infinity of c times b sub n is just going to be that constant times the value b. The limit as n approaches infinity of a sub n times b sub n is just a times b, And if we have a quotient, the limit as n approaches infinity of a sub n over b sub n, that is a over b as long as we're not dividing by 0. So again, even though we're dealing with functions with a discrete domain rather than continuous, all the same limit rules apply. Before doing some examples, let's recap. To determine if a sequence a sub n converges, we must evaluate the limit as n approaches infinity of a sub n. If that limit exists and equals L, the sequence converges to L. If that limit does not exist, the sequence diverges. In these examples, we want to determine if the following sequence converges or diverges. If it converges, determine what it converges to. Our general term is 2 to the n over n squared. So in all of these examples, we're going to have to find the limit as n approaches infinity of that general term, 2 to the n over n squared. Let's take a moment to remind ourselves of the laws of dominance, since these are all going to be as n approaches infinity. So let's recall that as n approaches infinity, the slowest growing type of function is going to be logarithms. And then after that, it's going to be polynomial functions. So they're going to grow just a bit faster than logarithms, followed by exponential functions, grow bigger faster than polynomials, and then factorials. So that in mind, we have an exponential 2 to the n over a polynomial n squared. So that exponential is going to grow bigger faster. So if the numerator grows bigger faster, then the whole thing is going to infinity, and infinity is not a real number, so this limit does not exist. So that means the sequence diverges. In this example, my general term is natural log n over n factorial. So I want to evaluate the limit as n approaches infinity of natural log n over n factorial. So we just mentioned how factorials grow bigger faster, and logarithms are actually the slowest growing. So even though both of these are going towards infinity, n factorial is growing bigger faster. So we want to be really extreme in our head. We want to think about if the bottom of a fraction is really big. So let's say 1,000,000 is in the denominator, and then let's make the numerator small. So we're just kind of, again, thinking, reasoning this here. So a small number like 1 over 1,000,000, that's really small overall. So that means that this limit is approaching 0. And 0 is a real number. So because this limit at infinity is a real number 0, the limit exists. So that means that the sequence converges. And furthermore, it actually converges to 0, the answer to the limit at infinity. For this sequence, we have a general term a sub n is equal to 3n to the fourth minus 7n squared plus 5 all over 6 minus 4n to the fourth. So we want to do the limit as n approaches infinity. Now looking at this, I have a polynomial over a polynomial. So they're the same type of function, but we want to look closer and recognize that they are polynomials of the same degree. So the leading term in the numerator is 3n to the fourth, and the leading term in the denominator is negative 4n to the fourth. So we're looking for the highest power. And so since they are the same degree, towards infinity, we can just take their coefficients. So towards infinity, basically, those smaller terms don't really matter. And n to the fourth, they are the same degree, so we can just take their coefficients to be negative 3 over 4. And that is a real number. So because it's a real number, we know that this sequence converges, and it converges to negative 3 over 4. Here we have our sequence given as a list of numbers. So we need the general term. First, we're going to have to find a sub n. So let's go ahead and think about how this first term is a sub 1, then a sub 2, then a sub 3, then a sub 4. We want to create our a sub n. I'm going to focus on the numerator first. So the subscript 1 corresponds to an output in the numerator of 2. The subscript 2 gives us an output of 3. The subscript 3 gives us an output of 4, and 4 gives us an output of 5. So the numerator is always 1 bigger than that subscript. So that means that the numerator's pattern formula is going to be n plus 1. Now let's take a look at the denominator. I have 3, 9, 27, 81. I can think about this as 3 to the first, 3 squared, 3 cubed, 3 to the fourth. So notice there that the exponent of 3 matches my subscript. So that means the denominator rule is going to be 3 to the n. Now, I've left a blank space in front here because I have alternating terms. My first term is negative, then I have positive, then negative, then positive. When I want to have alternating terms, I want to include a piece that is either -1 to the n or -1 to the n plus 1. And we kind of have to think about which one it's going to be based on if the first term is positive or negative. So let's think about how if I substitute in 1, -1 to the 1 is negative. So my first term will be negative. And then let's just check if we plug in 2, -1 squared, a negative power or a negative number to an even power is positive. So -1 to the n is going to work. If it didn't, if the first term was positive, then I would need to include -1 to the n plus 1 or n minus 1. Those are the ones that we're thinking about for making the terms alternate. That's the easiest way to make the terms alternate. So here, this is my general term, a sub n, is -1 to the n times n plus 1 over 3 to the n. And now I need to find the limit as n approaches infinity of that general term. But this includes negatives. And I had this theorem that said we can just look at the positive terms. And so we can instead look at the limit as n approaches infinity of n plus 1 over 3 to the n. And as long as that's equal to 0, then this limit is equal to 0. Well, it turns out 3 to the n is an exponential, which grows bigger faster than the polynomial n plus 1 on top. So this limit is equal to 0. Therefore, the alternating one is equal to 0. And since that's a real number, we know that our sequence converges. So I'm going to go ahead and sneak that up here. The sequence converges, and it converges to 0. This sequence is interesting. We have a general term 3 plus the quantity -1 to the n. So if we think about what's happening as n approaches infinity here, we have 3 plus -1 to the n. So the 3 doesn't have n in it. And here, as n approaches infinity, I'm going to substitute in values starting at 1. So 1, 2, 3, 4, 5. And so this is just going to keep bouncing back and forth between +1 and -1. So let's actually write out some of the terms in this sequence so we can kind of see what's happening here. So if the first number I substitute in is 1, 3 plus -1 is 2. That's a sub 1. Then a sub 2, -1 squared, that's going to be a positive 1. So 3 plus 1 is 4. And then if I plug in 3, -1 cubed, that's -1. So I have 3 minus 1 again, so 2. So I'm going to have 2, 4, 2, 4, 2, 4, and so on. So hopefully I can see that as n approaches infinity, these values are not getting close to any particular number. So this limit does not exist. And if the limit does not exist, then we say that the sequence diverges. For this sequence, we have a sub n is 1 plus cosine n over the square root of n. So we want to do the limit as n approaches infinity of 1 plus cosine n over the square root of n. Now here, when I gave you that list of dominance rules, we only looked at logarithms, polynomials, exponentials, and factorials. and none of those are included here. So in the numerator, let's kind of think about what we have going on. We have just a constant plus cosine n. And let's take a moment to remember how the cosine function alternates between -1 and 1. So basically the numerator here is acting like a constant, basically, because it's just 1 plus values between -1 and 1. So that's like a fixed number up here, basically a constant. And the denominator isn't a polynomial because polynomials have positive integer exponents, and this is n to the 1/2. But it is getting bigger. So as I plug in bigger numbers into the square root of n, that's still getting bigger, and the top is constant. So if the bottom is still getting bigger faster, right? So this one is getting bigger faster. The top is basically constant. Then the whole limit is going to go to 0. So that being said, we're going to have that this sequence converges, and it converges to 0. Now, just as a quick aside, we had the fact that logarithms were the slowest growing functions, and then next was polynomials. But I just want to share that in there is root functions. So logarithms like log base 2 of x is smaller than natural log of x because the base of natural log is e. And polynomials, again, have positive integer exponents, so like x to the first, x squared, x cubed. But in there is root functions. So in other words, like x to the 1/2 is smaller than x to the first, and x to the 1/3 is smaller than x to the 1/2. So that those root functions do fall in between the logarithms and polynomials. Now here we have a general term a sub n equals the nth root of n squared. So we want to think about this as n to the 2 over n. Now if we set up the limit as n approaches infinity of n to the 2 over n, well, 2 over n as n approaches infinity is 0. But there's an n in the base here. So what we end up with is this idea of infinity to the 0, which is indeterminate. And the way that we're going to have to evaluate this is using L'Hopital's rule. So what we're going to do is we're going to introduce a little way to rewrite it involving exponentials and logs. So we're going to have the limit as n approaches infinity of e to the natural log of n to the 2 over n. So what did we just do? We rewrote this in a clever way so that we could involve logarithms. So remember that e and natural log cancel, so these two are equivalent. But now what we can do is we can bring 2 over n to the front of the log right here. So we have the limit as n approaches infinity of e to the 2 over n times natural log n. Okay, so here's what I'm actually going to do. I'm going to do two things here. I'm going to bring the limit into the exponential. So I'm going to have e to the limit as n approaches infinity of 2 natural log n over n. So now I can really just focus on this limit right here using L'Hopital's rule. I do have an infinity over infinity case. And so I can use L'Hopital's rule. I can take the derivative of the top and the bottom. I can actually also just use dominance laws again because I have a logarithm on top and a polynomial on the bottom, n to the first. So that means that this whole limit is going to 0. So I have e to the 0, which is 1. So the answer to our limit is a real number, 1. So that means that the limit exists. And so this sequence converges, and it converges to 1. The last example and this next example would benefit if we knew these important limits. For any real numbers, a and b, if we have the limit as n approaches infinity of n to the a over n, that equals 1. So we actually just showed that using the technique from earlier, and then either L'Hopital's rule or the laws of dominance. Now we also have this limit as n approaches infinity of the quantity 1 plus a over n to the power of b times n, that equals e to the a over b, which can be shown similarly with the previous technique, but we're just going to now use this important limit to evaluate the next limit at infinity. On this problem, our sequence general term is a sub n equals the quantity n plus 2 over n raised to the n. So if we start to set up our limit as n approaches infinity of n plus 2 over n to the n, and we attempt to use the laws of dominance and recognize this is n to the first, so we can take their coefficients in the parentheses, we would get 1, but then n is in the exponent, so we would get 1 to the infinity, which is also an indeterminate form. So that doesn't quite work, and we can use that e to the natural log technique, but instead we can use our important limit just introduced. The idea that the limit as n approaches infinity of 1 plus a over n to the power of b times n equals e to the ab, as long as we rewrite what's inside here. So we can rewrite this as the limit as n approaches infinity of here, if we split this up, n over n is 1 plus 2 over n to the n. So now I do have this form where a is equal to 2 and b is equal to 1. So this limit is equal to e to the 2 times 1, or just e squared, which is a real number. So that means that this sequence converges, and it converges to e squared. So knowing this important limit can be very helpful at avoiding kind of that long way of introducing e to the natural log and then eventually using L'Hopital's rule.